Okay, so this lecture is about semiconductor packaging, and so I think this will be useful in some of the, especially the papers. If you're looking at the paper for controlling the power supply conditioning for silicon chips, I think this will be particularly useful. But generally, it's kind of a useful concept because what you'll probably typically come up with, like to actually see a semiconductor chip, is something that's already in a package. That's how you'll see the part typically. Okay, so this is kind of a picture of like a package. It's a little bit exaggerated, but you can see the silicon die in the middle. It's diced up. So literally what they will do is they will use a saw to saw a wafer along where the chips are in both directions and remove the silicon pieces that look like those little chiclets there, and they will put them in a package and wire bond it. So you can basically put it into a printed circuit board. So it becomes kind of a useful thing to work with. And that's what you typically see these packages. So there's a bunch of different package types that we'll talk about here in a bit. But so packaging has a bunch of different functions. Um, so the main thing is basically it allows you to plug this part into a printed circuit board. So typically what you do is the silicon chip with billions of transistors, etc. At some point, gonna want to use it, and the way to do it is solder it down onto a board. So you'd end up with a printed circuit board. It's got a bunch of stuff on it, and then maybe it has a connector on the side. That's kind of how you typically see it. And then maybe it's got your packaged part soldered down on there, and you can start using it. So one of the main uses of a packaging is that it allows you to electrically connect power and ground to the chip at the level of a printed circuit board, as opposed to on the very tiny level of what's on these parts. To do that, it needs to have very little delay or distortion. It basically has to do that without screwing up your signals coming and going too much. It does do it a bit, and we'll look at it, and depending on how fast you're running or how much power you're burning, etc. That might be a little or a lot. Second thing the package does is it's sort of the mechanical uh, protection and connection of the chip. So the silicon is pretty thin. It's about a millimeter thick thing. It's not very thick. It could be pretty like wide. It might be 10 centimeters wide and a millimeter thick, and you could end up scratching it. Lots of things could happen to it. So you want to basically also protect the silicon chip. It's also imagine in a manufacturing environment. It's not always a very like sort of nice, friendly environment. So you want to protect the chip. And then lastly, it basically removes heat from the chip. So one of the main things we've talked about as the limitations of semiconductors is the heat generated in the chip. So like removing that heat is very important, and it should be inexpensive to manufacture and test. Okay, so here's a few different types of packages, and so I would say so. Basically, these depend on what you want to do with your part. I think mainly we have got a couple of different forks in the road for a silicon package. So one of the first decisions you make or whether you want to have it to be what material it's made out of. So it could be made out of ceramic or plastic. There are some other options, but those are kind of the main ones. So this is ceramic is for chips that have high power consumption, sort of specialty parts, maybe aerospace, etc. And it's kind of can be kind of expensive. So it's really good at dissipating power. It's good at sort of electrical connections, and but it tends to be expensive. It tends to be pricey. So plastic is basically cheap. Okay, and so most of what you'll see in consumer electronics is going to be plastic or things like plastic. It's going to get packaged into something like this. Okay. Then once you go into either one of these things, the next decision you make, and you'd have to make it in both cases, is surface mount or through hole. So surface mount, through hole. Okay, so what does that mean? Well, let me write it inside here. So a through hole part, through hole. In that, you'll see the package having sort of actual pins that are fairly long sticking out of the bottom of the package. So for example, in this drawing, you see this pin grid array package. That's an example of a through hole. You see the actual pins kind of sticking out. Here's another pin grid array. You can actually see the pins coming out. Here's a dual inline package. The pins are sticking out this kind of, so like here, another through hole, through hole, through hole. Those are examples of through hole parts. And the idea is these will go into holes in a printed circuit board. So you would have designed your printed circuit board to have holes that match to this package. And then there's also connections on your printed circuit board, metallic connections that you have going to these signals and so on. And basically you solder these pins into these metallic connections and you get a through hole package. So through hole is really for when you want to manually put the part down. Then the board, and this typically means low volume. Okay. And then surface mount means that your package has something. It's either things coming to the side at the same kind of um, plane as the board, or basically there are so either or you get these sort of solder balls at the bottom of the package. Okay, and where you typically see that in these ball grid arrays. So like this is a Xilinx part, you can see these balls at the bottom of this thing. And here's something that the things are coming down the side. Again, you do use that as a surface mount. The idea behind this is you can use something called solder reflow to package this part on. You can't hand solder these things. You would basically have to put them through a soldering machine. So that it basically like solders it basically joins all the parts in the package to the printed circuit board at the same time. So this is what you typically use for high volume manufacturing environment. Okay, so those are kind of like this are these different. There's lots and lots of different choices of packages, different pin counts, different sizes, etc. But this is kind of how you make a decision. So you go down this sort of decision path, figure out what you need, and package them in different types of things. So now you got to put the chip into the package. This is a drawing, but I think, again, going to the web might give you a better idea. So the first thing you do is you have to take the wafer. If you guys remember, the silicon chip comes in the form of a wafer that maybe is not maybe, but it's 12 inches. It's either 12 inches or 8-inch diameter and about 1 millimeter thick. And the manufacturing place has basically printed all these chips onto this wafer. So indeed, it looks like um, this. So if you can look here, these are all, whoops, shouldn't have done that. These are all like individual die that are on the wafer. Okay. And then what you do is you take a saw, and it's not just any saw, this is precision saws in a manufacturing environment. They're called diamond saws. I guess the edges are made out of diamonds. Maybe because they're like can be made narrow and hard. And what they do is they basically cut through these parts. So you do all your vertical cuts first, and then you do your horizontal cuts, and then you basically all the die are sitting there, and then you can basically grab the individual die. So here you see, oops, what they've done is they've taken out individual die from after the part's been sawed. So you can kind of see these saw marks here as they've cut the parts, and now they can basically remove these chips from that. Excuse me. So then once you have these little silicon chiclets, so this would be like at the very center here, you can see the part that would be that thing in the center. They basically glue that into the center of your package. So initially you don't, this top part isn't there. This is a lid that gets on afterwards. So you basically glue that chip down, and then you have these things called wire bonding that there's very narrow, very, very thin wires that come down and bond from the chip to the package, and then they put a encapsulating layer on top of it. Here's another drawing from the web that kind of exaggerates that, but maybe here it is. So again, kind of an exaggeration, but shows you these wires going to the silicon piece in the middle here with the package that looks like a through-hole type of package here. Okay, so that's kind of a visual for what you would typically do. So anyway, let's see what else we got here. So there are many different types of packages, and like I said, break down into ceramic, plastic, through hole, or surface mount. And usually they're basically the idea behind which one to use. It's based on your heat dissipation and sort of electrical, mechanical sort of requirements. Okay, so let's first look at the electrical issues that you're forced with. So whenever you have stuff that you add, it's kind of nice, now you got a ability to deal with this piece of silicon at the printed circuit board level, which is nice. But you're adding so-called parasitics. Okay, so parasitics generally are kind of things you don't want in electrical engineering. So, for example, when you use, you have this pin, very large physical pin in the package that you're connecting to, this pin, so package pin, what you'd like, what you like is like a very low resistance connection for that very low resistance connection from the pin to the silicon. But what you'll end up with is actually you'll get some resistance, you'll get some inductance, you'll get some capacitance at various points, etc. So, and you get, the capacitance could be to another pin, it could be to ground, so who knows? So, so you end up when you have a chip, when you put your silicon chip in the package and you connect it up to the package pins, you end up with a bunch of this, um, with a bunch of these parasitics. Okay, so, and the parasitics mean different things to different types of chips. Generally, you have different types of pins. So typically, the pins that you have in a piece of silicon are divided into two types of pins. There are the signal pins, basically any input, any output, those kind of things, anything that's carrying information, and then power and ground pins. And it's kind of two different concerns and two different approaches. So let's look at the signal pins first. I think with the signal pins, you have the big worry you have resistances. You're actually are pretty low, and you usually don't. So resistance is usually not a big deal, not a concern in package, just because these metal pins are pretty big, big cross sections, low resistance. So what you're concerned about is inductance. So you can see these different pins have inductances. And then you have, so interpin capacitance is also a problem because this can lead to crosstalk. Okay, and then on the power and ground pins, basically you have kind of similar things, similar issues. Now, power and ground, you're more concerned about resistance. Although the resistance isn't any higher than this, but because you have so much current going into power and coming out of the ground, even a small resistance, let's say you have a very low resistance. So say this is zero point zero 0.01 ohm, which seems very small, but if you have if you have 10 amps on VDD going to your chip, which is very possible, the voltage drop across the pin maybe 100 millivolts, which is, you'd have 100 millivolts on the power, 100 millivolts on the ground. Your VDD is only 1 volt, so you've already eaten 20% into your power supply range, which is quite a bit, and problematic. Okay, so one of the things you can have this is for high-end packages, is you can have sort of decoupling capacitors built into the package. I'll talk about decoupling capacitors in a bit. And then if you do that, then you might have another sort of bunch of inductance to the board, basically. Once you get into the board, then you have to deal with other inductances and capacitance of the board. But this is basically what what it kind of looks like in terms of the electrical parasitics. Okay, so in terms of the heat dissipation, I think we've talked about this a bit, but these pieces of silicon, they're burning a lot of power in a very small surface area. So this slide is comparing the surface area, the power and surface area of a incandescent light bulb, so a 60 watt light bulb, which sort of dissipates that the heat from that power over 120 centimeters squared, compared to a sort of, this is an older microprocessor, but you get the idea. That's, is putting up, is trying to dissipate twice as much power in 30 times less surface area. So that kind of gives you an idea of the problem you had. And so heat dissipation is an issue. And sort of the heat dissipation, you have a few different ways of dissipating heat, but from the package to the ambient means ambient, sorry, means the environment. You basically, the primary way of removing the heat from the package, well, there's two ways. Sorry, excuse me. You have two ways of removing the heat. One is through conduction, so heat conduction. So, and then one is through the heat convection. In heat conduction, you've got the package soldered onto a board, and they're kind of the metals are touching through the connectors. You might have a metallic actual heat sink on the board connected to the package, and you're removing the heat through there. So that's conduction. And then convection is like, heat going into the air. And then you need to basically move air, so like with a fan or something, or maybe just, you know, sort of hot air rises and cool air comes in. So depending on how much heat you're trying to remove, that kind of ends up being one of the options. So again, in this kind of a convection situation, that's why, for example, some of your laptops have fans, so you can use fans to increase airflow. And then they have these fins that you guys may have seen on these parts. They kind of look like things like this. It's like a grid of fins all on top of this package. And basically, the idea behind that is you're able to remove heat. Basically, you're increasing the surface area. So fins increase surface area. Okay. So let's look at the heat removal. So I'm not, well, thermal engineering is something I don't know a huge amount about, but this is kind of the limit of my knowledge. But basically, what they use is a concept called thermal resistance that kind of works like, in some ways, it's the same way of thinking as like regular resistance. So the idea behind it is this equation. So basically, if you have a certain power consumption, let's say you have a part that's burning a certain amount of power, P. So power consumed by the part is P. Okay. And there's a certain amount of thermal resistance to, let's say, the air. Let's say this is air. Then you basically end up with a difference in temperature from the part to the air, and it's basically given by your power consumption times your thermal resistance. And you can just, if you have different things in series here, you just add up the thermal resistance of different parts. So the way that works out in a package or a chip is typically in a package, you have the package itself, and then you have the silicon chip, which is on the package with some epoxy. They've glued it down. So that epoxy itself has some thermal resistance, and the package has some thermal resistance. So both of those things you need to add sort of in series. And so here's an example of that works. And then, to control or to actually just measure, you don't really, I mean, I guess you can use it to control in a system point of view, but the temperature sensors are fairly common on the silicon, which basically means you have something that's measuring the temperature of your chip. You basically output that to the, let's say in the case of a laptop, you output that to your microprocessor, then, or sorry, to your system, and then the system decides that it's gotten too hot and needs to turn on the fan, say. Okay, so that's sort of the power or the temperature component of power. And now let's talk about the delivery of the power itself. So, one of the things, and this is going to one of the papers that you guys have, and I think is just an excellent paper about power distribution. Um, and basically, when you're looking at a silicon chip, so it might be, 10 centimeters on a side, but, might need like a current of, 10 to 20 amps of current on VDD. Just imagine all the parts that are all the gates that are all the switching elements, all the switches in there that are switching on and off. So they are gonna, in total, if you got 20 billion transistors, even if most of them are off at any given time, a bunch of them are on. So they're pulling current from the power supply. And another thing that's kind of really, there's two types of current that they're pulling. There's like in time, there is current that's flowing that's kind of DC current. But then more likely actually is that there's fluctuations in this average current as because you never know how many gates, or if you guys remember CMOS gates pull current and use up power when they switch. So you never know how many of them are going to be on, depending on the operating mode, depending on the data going through your chip. So in fact, the current on your supplies is is going up and down quite a bit. So you have a few different issues with current. So one of them is just the current, the average current that's going through your part, and the average current. So the average current, you have it basically usually have a resistance and an inductance in series with your supply. So VDD on board, on the PCB board, and the VDD on chip. So DC current will get a DC drop. So that's your sort of average current. You'll get a DC drop across this resistor. But even worse is if you have a change in this current, which you do all the time because of the way CMOS circuit works, you get a voltage, so delta V across your inductor, which is It's a function of the change in current as a function of time. And that's how you end up with these spikes because the current's changing as a function of time and you get this variable voltage. Okay, so there's some examples of the IR noise. And the primary way you have of trying to limit the these spikes caused by this change in current as a function of time is decoupling capacitors. And so this is one of the things you guys will run into using chips is, let's say you have your chip, you might have your power, you might have a wire bond going to the chip that's going to have its own, so this is wire bond inductance. And then this is going to the package, and then the package might have its own inductance, so package pin inductance. And then this goes to the board, and then the board to connector might have its own inductance to connector inductance. And so all these things as you get LDIDT are going to be problematic in terms of voltage drops across each one of these. So typically what you do is you put charge reservoirs in the form of capacitors. In the form of decoupling capacitors, and you use those to basically supply your current. And you end up with, because there's different speeds, and this is kind of like leading up to the paper, and my next sort of conversation is going to be about that paper, is going to basically look at how you can use these different decoupling capacitors, different frequencies, etc., to decouple.